In addition to the average value and sample standard deviation, another useful parameter we can calculate from our measurements is the adjusted Fisher-Pearson standardized moment coefficient, commonly known as the skewness coefficient, denoted by capital G sub 1. So why does this coefficient matter? Well, it quantifies our data asymmetry. For example, if the distribution is perfectly symmetric, like a bell curve, the skewness coefficient is 0, meaning our data is symmetric around the average value. But if the distribution is skewed left, meaning the tail extends to the left, then the skewness is positive. Similarly, if the distribution is skewed right, the skewness is negative. The more the data leans to one side, the larger the absolute value of this coefficient. So when the absolute value of the skewness coefficient is small, the average value is a good measure of the central tendency of our measurements. But when the data is strongly skewed, another measure of central tendency might be a better choice, such as, for example, the median. That's why this coefficient is useful. Now how do we calculate it? Well, we can use the following formula. G1 equals n divided by n minus 2 times n minus 1 times the sum of x sub n minus the average value divided by sigma, all that cubed, where little n goes from 1 to big N. This formula looks complicated at first, but it simplifies when we rewrite it in terms of the z-scores as n squared over n minus 2 times n minus 1 times 1 over n times the sum of z sub n cubed, where little n goes from 1 to big N. Here, z sub n is the z-score of our nth measurement and is defined as the nth measurement minus the average value over the standard deviation. The z-score is simple to interpret. It tells us how far a measurement is from the average in terms of standard deviations. This becomes evident by writing x sub n minus the average equals z sub n times the standard deviation. Graphically, the distance between our measurement and our average is equal to the absolute value of the z-score times the standard deviation. Also, if the measurement is greater than the average, its z-score is positive. Likewise, if the measurement is less than the average, its z-score is negative. But if the measurement is equal to the average, its z-score is 0. That being said, we can now notice that the skewness coefficient consists of two parts, a bias correction factor and the average of the cubed z-scores. So just like when we use Basel's correction of n-1 instead of just n to correct the bias in the sample variance calculation, the first term here corrects the bias in our skewness estimation. This can be proven by finding the limit of n squared over n-2 times n-1 as n approaches infinity. This is equal to the limit of n squared over n squared minus 2n minus n plus 2 as n approaches infinity. Let's quickly rewrite this expression where minus 2n minus n is replaced with minus 3n in the denominator. Using L'Hopital's rule, this expression can be written as the limit of 2n over 2n minus 3 as n approaches infinity. Again, using L'Hopital's rule, we can write the limit of 2 over 2 as n approaches infinity, which is simply equal to 1. So the bias correction factor that we use to multiply the average value of our cubed z-scores gets closer and closer to 1 as the number of measurements increases. In other words, the more samples we have, the less this bias correction factor affects the skewness coefficient. Alright, now let's answer the question, why are we calculating the average of cubed z-scores? Why the third power here instead of the first or the second? Well, if we use the first power, the result would always be 0, since the average of all z-scores of a measurement set is always 0. Let's quickly prove this. We can start by writing 1 over n times the sum of z sub n, where little n goes from 1 to big N, equals 1 over n times the sum of x sub n minus the average over the sample standard deviation, where little n goes from 1 to big N. This equals 1 over n times the standard deviation times the sum of x sub n, where little n goes from 1 to big N, minus the sum of the averages in the same range. This can be simplified as 1 over n times the standard deviation times n times the average minus n times the average which is equal to 0. Now let's compute the average value of the squared z-scores. This is equal to 1 over n times the sum of x sub n minus the average divided by the standard deviation, all squared, where little n goes from 1 to big N. This can be reformulated as 1 over n times the sum of the squared differences between our measurements and our average, where little n goes from 1 to big N, divided by 1 over n minus 1 times the same sum. Since the two summations cancel out, this is equal to n minus 1 over n, and this is just a positive constant that doesn't tell us anything about the skewness of our measurements. So it turns out that by using the average of the cubed z-scores, we can finally quantify the skewness of our measurements. But how skewed is too skewed? Unfortunately, that depends on several factors and the specific application. If the data is largely skewed, you should consider switching from an average to another measure of central tendency, such as for example the median. But if the data is only slightly skewed, the average might still be fine. On the internet, you'll often find people saying that the rule of thumb is that the acceptable skewness coefficient value is between -1 and 1. I put a link in the description of the video where you can find such a statement. But where does this rule of thumb come from? Well, this graph can illustrate that nicely. This is the graph of f of z equals z, and this is the graph of f of z equals z cubed. These two curves intersect at 3 points, 1, 1, -1, -1, and at the origin. When the absolute value of the z-score is below 1, the absolute value of that z-score cubed is even smaller. But once the absolute value of the z-score exceeds 1, the absolute value of that z-score cubed grows quickly. So skewness becomes quite sensitive to large asymmetric deviations. And that is why the absolute value of the skewness coefficient should not exceed 1. Now, before ending this video, I would like to point out one important thing. All of these parameters, the average, the sample standard deviation, and the skewness coefficient, they only make sense for unimodal distributions where there's just one main peak. If the data is multimodal, for example bimodal with 2 peaks, these statistical parameters can be misleading. Estimating the number of modes goes beyond the scope of this video, but it's important to keep this limitation in mind. That being said, let's switch to the next video where I will show you how to efficiently calculate the skewness coefficient online. Thanks for watching, I hope this video helps.